sorry. I was talking to Anuradha. I mean,
Hello, Krishnendu. How are you?
Hi.
After a long time.
Yeah, after a long time. How are the children?
Children at the moment are fine, but we don't know when their school will start now. So same, they may start from January and still it will be a dilemma only whether to send them or not.
Yeah, ours is starting this week and we are in a big dilemma because...
Correct.
Yeah.
There are a lot of cartoons for young children. So there is one famous Marathi cartoon called Chintu, in which they go to school and then the child comes back home and the mother asks, "Where is your mask?" Then he says, "We have exchanged it today. I have exchanged it today with my friends."
Yeah. Okay, so I think it's 4 o'clock. So John probably would like
to. Okay, so I should start.
Yeah. No, I think first Anuradha may introduce.
Yes,
yeah. Okay.
Katre sir, should I begin?
Yes, please begin. Yes.
Okay.
This time.
So a very good afternoon to everyone and a warm welcome to the speaker of today, Professor John Parker from Durham University, UK. A warm welcome to all the interested listeners also. Professor Parker is not new to this seminar and he has already given 2 talks in September. His area of research is mainly that of hyperbolic geometry. Still, for some of us who are joining a bit late, I think we need an introduction, so I will do that quickly. Today, he will be talking about the definition of an arithmetic group following the 1968 article by Vinberg. The article is on discrete groups generated by reflections in Lobachevsky spaces. He will connect this definition to triangle groups and discuss Takeuchi's theorem. Professor Parker, we look forward to your talk and we also look forward to explaining the connection that you have said in your abstract about the quadratic form method and the quaternion algebra method used by Takeuchi. Welcome again to everyone and I request the speaker to begin his talk. Thank you.
Thank you very much indeed for that lovely introduction. Once again, it's a great pleasure to be speaking to you. I have enjoyed preparing these talks. Unfortunately, because of my duties, I've not been able to be at other people's. You will also notice that there is a certain amount of overlap with Bram Petri's talk from last week. And he and I have discussed what we were going to say. And I think that hopefully you can think of this as being like stereoscopic vision, where you get 2 different viewpoints on the same thing. Okay, so let me begin. So I'm talking about arithmetic groups and Takeuchi's theorem. So the plan is I'm going to give a brief introduction. Then we're going to have a little bit of background on Galois theory, because the main idea is a lot of number theory in here. I'm going to give you the definition of arithmeticity. And then I'm going to give you 2 different descriptions of arithmetic triangle groups. The first via quadratic forms, which, as has been just introduced, is following the method of Vinberg. And the second is more following Takeuchi using quaternion algebras. And I will try to connect the 2. My personal preference is the quadratic forms approach, and I believe also that Bram Petri talked about quaternion algebras, so I shall not go into too many details there. I don't want to repeat what he said. So let's start with the introduction. So there are 3 main references for this. Just a moment, my pen seems to have stopped working. Yeah, good, thank you. So let me try that again. There are 3 main references. So I'm going to be following this paper of Vinberg, or at least some of the methods that are outlined there. Takeuchi gave a general characterization of arithmetic Fuchsian groups using quaternion algebras in this paper. And then a couple of years later, he applied this to triangle groups. So the main theorem that we're going to be going to lies in this second paper of Takeuchi. And the two different approaches will follow the two other papers that I've listed there. So let's just remind ourselves what a discrete group is. And I hope that this will be a familiar definition for everybody. A group is discrete if it carries the discrete topology. What does that mean? It means that for every element of the group, there is an open neighborhood, so that it's the intersection of that open neighborhood with that particular group element is the identity. So there are no other group elements that come close to it. And equivalently, every convergent sequence of elements is eventually constant. Now, there's one particular example of a discrete group that we have all known since our earliest childhood, and that is the integers sitting inside the real line. So the first time we started to do adding up at elementary school or measuring things with a ruler, this is exactly what we were doing. And it's a very, very simple idea, and that is at the heart of everything that we're going to talk about today. And we'll see that it has quite profound consequences. So this example of the integers inside the reals is really the main tool that we're going to be using. So for example, to see what this is about, the modular group PSL2Z, which we've met before, now that's a subgroup of PSL2R. And we can think of the geometry of its action, and we can think of why it's discrete. Now, there's a wonderful book by Magnus, which is based around the illustrations in the book books by Fricker and Klein. And Magnus has this example of the modular group. And he says it's completely obvious that the modular group is discrete. When I was first a graduate student, I read that statement and I thought, yes, I know how to make a fundamental domain for the modular group, and I know how to show that that really is a fundamental domain, and therefore to conclude that the group is properly discontinuous and therefore discrete. And I had completely missed what Magnus was trying to say. This group is discrete because the integers are discrete in the reals. If I were to consider a sequence of elements of PSL2Z, then I could write them as a sequence like this. And then I could map them over to Z4 sitting inside R4. Now Z4 sitting inside R4 is discrete, and therefore PSL2Z is discrete. And that is an idea that we're going to see again and again and again through this talk. But if it was just that we had to do linear combinations of things over the integers, then our life would be really easy. So let's just look at something which is not discrete. So I'm going to consider the ring, this is the ring of integers in Q adjoin root 2, but you can just think of it as a ring sitting on its own for the moment, where I take linear combinations, integer linear combinations of 1 and root 2. And something I think that probably many of our first year students will understand is that this is not discrete, if they assume that we know what discrete is. But the way we can really show this properly is using Diophantine approximation and continued fractions. So I can construct a sequence of rational numbers so that this sequence of rational numbers tends to root 2 as n tends to infinity, and it tends in a very strong way. It tends very fast to root 2. So the difference is less than 1 over qn squared. And this is done by continued fractions. And I'm going to brush lots of the details under the carpet because we don't really have time for that. But I'm just simply to say that you can start out with 3/2, which is slightly larger than √2, and 7/5, which is slightly smaller than √2. And then you can construct a sequence iteratively using this particular equation. And secretly, what's happening behind the scenes is the continued fraction expansion of √2 is 1, 2, 2, 2, etc. But that doesn't really matter. You can think of other ways to show that √2, that m plus n √2 is not discrete. However, let's just do something slightly strange. Let's not just think of our m plus n √2, but I'm going to think of it, think of a pair. I'm going to think of m plus n √2 in the first coordinate in R2, and in the second coordinate, I'm going to think of m minus n √2. And I can, of course, factorize this so that I'm having m times the vector 1, 1, and n times the vector √2 minus √2. And now the image of this is discrete. It's a lattice. So let's just sort of draw a little picture of what this is looking like. So we're going to have, well, 0, 0, and m and n are both 0. We're going to have 1, 1, and somewhere up here we're going to have whatever it's going to be. Okay, maybe let's put this one here. This is minus √2, √2. This one up there was 1 minus √2, 1 plus √2. And I'm running out of space, but you can see that I could sort of draw little rectangles there, and this would tessellate the plane. So what have I done? I've taken a non-discrete ring, and I've done this strange operation by moving up one dimension, and now I've got something that is discrete in R2. Of course, in this little picture I've drawn, if I were to just project everything down onto the x-axis, I would just recover my m plus n √2, and I'm saying that this is not discrete. Effectively, what I'm saying is, if I take this sequence of rational numbers, so that Pn, or sequence of Pn Qn, so that Pn minus Qn √2 tends to 0, then Pn and Qn have to get very big, and they have to get very big in a sort of independent way, so that I would be moving very far away from the x-axis in the y direction. That just takes a little bit of thinking about. But this idea is going to be at the heart of what we're doing. So I really want to just take some time and just repeat what I've said. We're taking this non-discrete ring, we're then doing this strange thing with the m minus n √2, and then I'm turning it into a discrete subset of R2, which is not where I want it to be, but it is discrete. So let's now move away from my introduction and start to think about a little bit of Galois theory. And I'm going to do a little background on number fields and some very basic ideas in Galois theory. So a number field is a finite extension of the rational numbers. It's a field, finite field extension of the rationals. An algebraic integer alpha is the root of an irreducible monic polynomial p with integer coefficients. And I can always take p to be the polynomial of smallest degree, in which case it's called the minimum polynomial. These are very standard definitions from algebraic number theory. And it's a fact, it's a theorem that for any number field, this should have been a number field here, that we can find an algebraic integer alpha so that I can write k as q adjoin alpha. So what do I have to do? I have so this idea that I have this minimum polynomial, it means I can write I can write alpha to the d as some linear combination of lower powers. So minus a0 minus a1 alpha minus a d minus 1 alpha to the d minus 1. Well, in fact, all of the a's there are integers. So this is going to be a finite extension. I only need to add the d minus 1 powers of alpha into it. Okay. And so now, because I have, wherever I was, I have this algebraic integer, it has a minimum polynomial. So that minimum polynomial has roots, possibly over the complex numbers. And so it's going to have d roots. Maybe we have some repeated roots. If we had repeated roots, it wouldn't be of minimal degree. And so actually, we don't have any repeated roots. Okay, so then we've got this minimum polynomial. And I'm going to make an assumption that this number field is what is called totally real. So this is k is totally real, meaning that all of the embeddings into the complex numbers are real, or effective, or equivalently, all of the roots of the minimum polynomial of alpha, they're all real numbers. Now, what I could do is I could adjoin any one of those other roots of the minimum polynomial to Q, and I would get another number field. And actually, it's isomorphic to K via the Galois automorphism that sends alpha to alpha I. And I'm always assuming that alpha 1 is equal to alpha, so sigma 1 is the identity. Okay, so I have a number field, which is, I'm going to assume it's an extension of degree d over Q. I can write it as Q of alpha. Alpha is an algebraic integer, and so there's a minimum polynomial. I've got alpha 1, which is alpha, all the way through to alpha d, the roots of the minimum polynomial, and therefore I have d different automorphisms of k to itself, obtained by moving alpha to one of the other roots of the minimum polynomial. Moreover, the set, if I were to take, I'm now going to think of, so that's sort of up to this line, and then suddenly we have a bit of a leap. What I can do is I can now think of taking all of these embeddings all at once. Now I can form this vector, which would be in RD, alpha 1 through to alpha d. Of course, I can take other powers of this. I could take 1 all the way 1, where I've got my power is just 0, all the way through to alpha 1 to the d minus 1, alpha d to the d minus 1. And I claim that that is a basis for R to the RD. And again, that's a little exercise. You can find it in any book on algebraic number theory or Galois theory. So now let's put my previous example back into context here. So the square root of 2 is an algebraic integer. It's the root. It's a root of x squared minus 2. That's its minimum polynomial. And so I could write Q adjoin root 2 as in that way. I can write it as linear combinations over the rationals of a and of 1 and root 2. Now there's a second root to the minimum polynomial, which was minus root 2. And so I have a Galois automorphism of k, which sends root 2 to minus root 2. And so there's one trivial automorphism sending root 2 to itself, and a non-trivial one sending root 2 to minus root 2. And so that's what this business of replacing the root 2, oops, I seem to have gone to root 2 to the minus root 2 in the previous examples, that was all about. And then we've just seen that pair of vectors is a basis for R2. So this, I'm sorry, this is going to get sort of quite a bit of theory to go through here. I'm trying to go through quite slowly. But what I want to now talk about is rings of integers in number fields. Okay, so let's suppose we've got a number field, Q of alpha. Suppose that it's totally real. That means that alpha 1 through to alpha d, the roots of the minimum polynomial of alpha, are all real. And now the set of algebraic integers in K is a ring, subring. Just like we saw Z adjoin root 2, integer linear combinations of 1 and root 2, that's the ring of integers inside Q adjoin root 2. Now, there exists an integral basis, beta 1 through to beta d, so that any algebraic integer in OK is an integer linear combination of the beta k. So it's not in general the case that the betas are all powers of each other, so we just need to get away from alpha. A priori, beta and alpha may not have anything to do with each other. But what I can do is I can apply this Galois automorphism, the thing that sends alpha 1 to alpha j, and I'm going to apply this to all of the betas, and I'm going to get another integral basis. It's not hard to see that if one of them was an integral basis doing the automorphism, the other one should be. And so that means that if beta, which is an algebraic integer in there, was this integer linear combination of the betas, then its image under the Galois automorphism sigma j is the same linear combination, or the same coefficients, but with the new basis, the beta upper j's. And so now what I can do is I can take the vector in Rd, consisting of all of beta and all of its images under the sigmas. And now I can write this, I can write each one of these betas as an integer linear combination of the respective integral basis. The coefficients are the same, so I can pull them out. And so I get an integer linear combination of vectors in Rd. And I'm going so that this is going to give me a map phi, which is going to go from, well, it's going to map from k to d copies of k. And I'm going to do that. Well, maybe I've got this map here is actually written in terms of OK, but that's okay. That's fine. Maybe I should have had OK there. The image of OK, so this is just like we saw with the Z adjoin root 2. This is a lattice in Rd. This is a discrete group which has finite co-volume. It's a copy of Z to the D sitting inside R to the D. So maybe I can say copy Z to the D contained in R. And the Z to the D are exactly these coefficients out front. So let's come back to our running example then. If I've got K is Q adjoin root 2, then the ring of integers is Z adjoin root 2. We have an integral basis 1 root 2, and then I have this map which is given by taking rational linear combinations of 1 and root 2 to themselves and the image under the Galois automorphism. And then I can restrict this to the ring of integers, and I get back exactly what I had before. So this long and complicated description I've just done over the last 2 slides is a way of abstracting all of the things I talked about this simple example to do this in greater generality. Right. I'm going to give you a second example, which is going to be pertinent to what we're doing today. So if we've got the Chebyshev polynomial, and actually I've slightly modified my Chebyshev polynomial, but it's the polynomial so that if I apply so it's a Tn of x, but if I evaluate that at 2 cos theta, then I get 2 cos n theta. And that's an integer, it's an integer monic integer polynomial. And that's not too hard to see. You can basically use de Moivre's theorem, and then sine squared is 1 minus cos squared a number of times, and you find that. So that's a good polynomial. So 2 cos theta is, or 2 cos 2 pi of an n, sorry, is an algebraic integer. It's a root of the polynomial Tn of x minus 2. However, this polynomial is not the minimum polynomial of 2 cos 2 pi over n. Notice, for example, that if I had put theta is 0 in here, then I would have got, and I evaluate there, well, I would get 2 cos theta, 2 cos 0 is 2 cos 0. In other words, 2 is a root of this polynomial. So that, let's just say x minus 2 is a factor. But there will be an irreducible factor, excuse me, with 2 cos 2 pi over n as a root. And I'm going to call that p of x. So this is going to be the minimum polynomial of 2 cos 2 pi over n, because it's the lowest degree polynomial dividing this one, and there's a uniqueness of minimum polynomial theorem. It's got order phi of n over 2, where phi of n is Euler's totient function, which measures the number of integers less than n co-prime to n.
What is order here? It is degree of polynomial.
Sorry?
What is order? Order.
I can't hear you.
What is order here? Order is degree or something else?
So sorry, can you, I'm having difficulty hearing you. Can you?
What is order here? Phi n by 2. What is order?
So phi n of it it's got order phi n of 2. That's basically because because 2 cos theta is the same as 2 cos of minus theta. We're picking up everything. We're picking up the minus signs as well. So right. So what would I expect to have? Maybe I would expect to have, 2 cos 2 pi over n, 2 cos maybe 2k pi over n, all the way through to 2 cos 2n minus 1 pi n minus 1 pi. I'm sorry, this is not working. 2 cos 2n minus 1 pi over n. So this would list, if I listed all of the things co-prime to n, I would get 1 something all the way through to n minus 1. However, this one is the same as that one, and in terms of the cosine. And so I'm only getting the first half of them.
Yeah, he only wanted to know whether it is degree of that polynomial.
Oh, degree, sorry. Yes, degree. Degree of a polynomial and the order of a polynomial for me are the same thing. I'm sorry. Thank you. I somehow the connection wasn't good. I could hear you, Krishnendu, very well. Thank you. Okay. So the other roots are the things of the form 2 cos 2k pi over n, where k and n are co-prime, and k, I should have said, is k is less than n over 2. Maybe equal to. Okay. So then it's a fact that if Kn now is the field where I'm adjoining 2 cos 2 pi over n, then the ring of integers is z adjoin 2 cos 2 pi over n. And an integral basis is this. So that's a theorem. It's not at least to me, it's not entirely obvious. Let's get rid of this scribbles down here. So that basically sets us up very similar, in a very similar way to the things we were setting up before. Okay, so for example, when n equals 7, T7 is this polynomial. And so we see that the minimum polynomial of 2 cos 2 pi over 7 is this factor here. And it has roots 2 cos 2 pi over 7, 2 cos 4 pi over 7, 2 cos 6 pi over 7. So you might think that it would be, that you might get something if you just took away x minus 2, that could be good enough. Well, let's just think about the case when n equals 9, and we take away the x minus 2. We also have 2 cos 2 pi over 3, so that would be x minus 1. So we also have that factor, and we get a minimum polynomial here, and you see that the roots there. Right. Okay. Maybe that was quite fast going through all of this algebraic number theory. This is why I asked people, or told people, that it would be good if they read a little bit up on that beforehand. Okay, so now what I'm going to do is I'm going to combine all of the things we've just done with something rather similar to that example on the very first slide of SL2Z. So I'm going to do the usual thing. K is a number field, ring of integers OK, degree of K over Q is D, sigma 1 through to sigma D Galois automorphisms, and I've got a map from phi from K to KD, being alpha goes to sigma 1 of alpha all the way through to sigma D of alpha, just like we had on the previous things. So now let's suppose that Q is a quadratic form whose entries lie in K. Because its entries lie in K, I can apply any one of these Galois automorphisms to Q, and I get a new form, Qj. And now let's consider this group here. The group which is the unit determinant n by n matrices whose entries lie in OK, and who also preserve the Hermitian, the quadratic form Q. And now, of course, applying the Galois automorphism, then I get a similar thing with a Qj instead of a Q. And what I can do is I can extend this map phi that we had up there. I can extend it to these.
So John, the Galois automorphisms, by that you mean the embeddings of K into C into complex numbers?
So yeah, I'm thinking of them.
The Galois automorphisms of what?
I'm thinking of K. So I'm thinking of K as actually. I'm thinking about it as being a particular real embedding of that field. And then I'm each one of the Galois so I can write it as Q adjoin alpha, and then sigma j sends alpha to alpha, which is alpha 1 to alpha j.
So K is not necessarily a normal, right? K is not a normal extension, but it has different embeddings in the complex numbers.
So I'm assuming that it's totally real, and so all of these embeddings are totally real, I should say.
No, that's okay. Oh, so these are the different embeddings into R.
Yeah. And so all of the embeddings are into R. Sorry, I should have said I'd assumed it was totally real a couple of times previously. I should have actually included it here. So all of these embeddings are so then Just gonna move this down. Q of alpha j is contained in R for j. Yeah, otherwise I would no longer have quadratic forms, because I may possibly have something over the complex numbers, and we would get all sorts of things happening. Okay, so I've got this map which takes which basically takes the different real embeddings, so the alpha going to alpha 1 through to alpha d. Excuse me. And I had this map that sends k to k d copies of itself. I'm now going to take this map. I'm going to take this matrix A that lives in well, I can, at the moment it's just going to live in SOQ, and I'm going to have the different copies of itself where I've performed all of these automorphisms. And now I'm going to also think about gamma hat. So gamma hat is the one where I've restricted the entries to lie in OK. Okay. Now, phi of OK is a lattice in RD. And so therefore, gamma hat is a lattice in this big product of orthogonal groups. So if you want to think about it, you can think of, instead of taking just this one matrix, I'm replacing that matrix by a vector, which is an integer linear combination. And this is probably the main statement here. The main thing that's going to drive what we're doing later. If this new quadratic form Qj excuse me, is positive definite for all of the non-trivial automorphisms, so for 2 up to j, or for just one of those j's, then this is compact, right? Because it's basically being rather like SON or SOD or something. And so now I'm going to assume that that's the case for all of these, or all of these non-trivial ones. And I want to show that this group gamma here is discrete. So let's do this slowly. So let's suppose that I've got a convergent sequence of distinct elements, I should say distinct, in gamma. Oh, well, okay. The way I phrase it, I don't need to assume distinctness, because I'm going to show that they're not distinct. Right. Okay, we've got this convergent sequence in gamma. Now I'm going to lift it up to this gamma hat by taking copies, lots of these other copies. Now each one of these AKJ, okay, that's now going to be living in gamma upper j. Because this group is compact, that's got a convergent subsequence. So I've got a whole bunch of d-1 convergent subsequences. I take a common convergent subsequence of that, and so I really just want to think of some subsequence of AK. So let's just throw away everything that is, but so I may as well assume that this phi hat of AK is convergent. Because this is a lattice up here, that's eventually constant. And so moving backwards, unwinding everything, my original sequence was eventually constant, and this group is discrete. So that's the argument for showing this is for showing this is discrete. So I'm now going to frame this in a slightly more abstract way that captures all of what I've just done. And so this is the definition of arithmeticity. So this is, we're going to start with a linear algebraic group defined over the rationals. So what is that? That's a group of m by m complex matrices. and its coefficients have to satisfy a set of polynomial equations whose coefficients lie in Q. So what are examples of these polynomial equations? For example, we could require that the determinant is equal to 1, because the determinant is a polynomial in the various entries of Q with coefficient of the matrix with integer coefficients. We could also assume that the entries lie in a number field. Because effectively what we're doing is we're saying that they're linear combinations of something that satisfies a monic integer polynomial. So that's another one of those polynomial equations. And we could assume that it preserves a quadratic form. And we've just seen that the example we have previously, that had all three of those sorts of polynomial equations. But these are just polynomial equations. And that's what a linear algebraic group is. So this definition is going to be, it's going to work for all linear algebraic groups defined over the rationals. If you want to think of something slightly more concrete, you can think about 2 by 2 matrices with whose entries lie in Q adjoin root 2 and who have determinant 1. So let G sub Z be the integer points in here and GR be the real points. Now, this effectively, previously I had OK, but what I'm doing here is I'm making this M much bigger by thinking of each one of those the entries as being another smaller block. That's called restriction of scalars. It doesn't really matter, but it effectively means that the what we had before is an example of this. Then this is an arithmetic subgroup of GR. GZ is an arithmetic subgroup of GR. Simply, this is the most jazzed up version of the integers are discrete inside the reals. I'm not really interested in this full generality for many of the applications that I want, so in particular for triangle groups. So I'm going to think of if I have a semi-simple Lie group G, and then I have, which I want to be thinking of arithmetic subgroups in here. You can think of here as being, I could think of SL2R, I could think of SO N1, and so forth. And then we take, we want to project down from our big abstract linear algebraic group down into our friendly small Lie group. And I want to do this with a continuous surjective homomorphism who has compact kernel. So on the previous page, that was exactly this business of coming up into this big group here, which was all of my products of my SONs, and then projecting down just onto the first factor, and the kernel of that projection being the product of all these compact groups, and so that was compact. Then a subgroup of G is called arithmetic if it's commensurable with the image of this arithmetic subgroup of GR. Now, what is commensurable? That's the natural invariant associated with arithmeticity. And it says that two groups are commensurable if their intersection has finite index in each of them. But I could also relax that. I could also conjugate one of them around in the ambient group, and then say the intersection of the group and the fixed conjugate of that other group that has finite index in both of them. And then big theorem of Burrell and Harishchandra that arithmetic groups are discrete and their quotients have finite volume. In the parlance, this means that they're lattices, but I haven't really defined lattices other than in Rn. So that's And so the example I just worked through earlier on, that was exactly working through this same construction, and so that is an example of an arithmetic group. Good. Well, I'm way behind time, so I'm going to perhaps have to speed up a little in order to finish. I'm sorry. This took a lot longer than I thought. Right. So we're going to go back into the world of triangle groups. So remember from my previous talk and many of the other talks you've had, if we've got a hyperbolic triangle with angles pi over p, pi over q, pi over r, and where p, q, and r are integers or possibly infinity, when one of those angles is 0, the triangle has an ideal vertex. And now I'm going to let delta be the group generated by the reflections and the sides, and gamma with the index 2 orientation preserving subgroup of delta. It's not going to particularly matter whether I'm going to be dealing with delta or gamma, but sometimes it's useful to do one or the other. And so I want to be able to write down matrix generators, and it's really useful thing is to have a specially adapted basis. We saw this last time when we talked about the Gram matrix, excuse me. And so I'm going to write, just because of the space, I'm going to write CP as cos pi over P, CQ as cos pi over Q, and so forth. And I'm going to define a number field, which is Q adjoined 2CP, 2CQ, 2CR, and that's going to sit inside one of these cyclotomic number fields that we already saw with the Chebyshev polynomials. And then I've got the ring of integers in here, and that's going to be what you would expect. So now the Gram matrix G, well, 2 times the Gram matrix, then that is a matrix in GL3, and its entries lie in this ring of integers. And it's easy to see that this is positive definite. Well, I say it's easy to say it's positive definite if and only if its determinant is positive. Well, let's just think about what it would mean. So you can see that the trace is equal to 6, which is positive. So that's the sum of the eigenvalues. So the sum of the eigenvalues is positive. And so if it is not positive definite, then it can only have 2 positives and 1 negative. So yeah, it has to have an even number. I'm saying this badly. So it can either have 2 positives and 1 negative eigenvalue, or has to have 3 positive eigenvalues. Anyway, it's positive definite if and only if this determinant is positive, and that's exactly what this for. You're going to recognize this again and again. So just remember that formula. Okay, maybe let's just say what I'm trying to say again. If this determinant is 0, then the matrix would have to have a 0 eigenvalue, and so it certainly could not be positive definite. If it's negative, then it can't have 3 negative eigenvalues, so it has to have 2 positive eigenvalues and a negative one, and therefore it's yeah. I'm getting too stressed about time. Move on. And a little exercise on the definition of a reflection tells us that if I take the orthogonal vectors to the mirrors as 1, 0, 0, 0, 1, 0, and 0, 0, 1, and then I write down what a reflection would have to be using the Gram matrix as my quadratic form rather than the usual quadratic form, then I get matrix generators for delta that look like this. And you'll also notice that their entries lie in, that they're all these algebraic integers, so they lie in the ring of algebraic integers of my number field. And so now I'm in the sort of setup where I can check for arithmeticity. So if I have a non-trivial Galois automorphism of this field, or rather, the first real embedding of this field, or whatever, and then I take the associated gram matrix, in order to check for arithmeticity, all I need to do is to check whether the new quadratic form is positive definite or not. And that's the same as checking whether or not my determinant is positive. Right? And so then I've reduced the business of arithmeticity down to just checking whether this expression, which we've seen, or its automorphisms, whether that's positive or not. Well, actually, if you're careful, you'll spot that I could find some automorphisms of the field that where things would go a little bit wrong. So it could be that I have something where CP goes to minus CP, CQ goes to minus CQ, and CR stays the same. Then this expression does not see that, and so there's something I need to do a little more than that. And this is one of the things that you get from Takeuchi and the people who've done arithmetic theory. So let's look at this subfield LPQR, where instead of just adjoining 2CP, 2CQ, 2CR, I adjoin the squares of the three generators and their product. And again, this is going to sit inside some cyclotomic number field, Q adjoin 2 cos 2 pi over n for some n, where n is the least common multiple of P, Q, and R. Right? And now it turns out that to check arithmeticity, we only need to check automorphisms that are non-trivial on this subfield. And so I can give you the statement of Takeuchi's arithmeticity theorem. This was the thing that's contained in, well, his point of view is using quaternion algebras, but I'm restating it in this form. So we've got a hyperbolic triangle. We find the reflection group. We find the number field associated to it. We find the subfield I've just taken. And then this group is arithmetic if and only if for every Galois automorphism whose action LPQR is non-trivial, this determinant is positive. That's a summary of everything that I've just said. And Takeuchi then goes on to say that there are finitely many arithmetic triangle groups. What he effectively does is he shows that if the lowest common multiple of P, Q, and R is sufficiently large, then this determinant, there is an automorphism for which this determinant is negative, and then he has to just do a computer search. And actually, it's quite interesting that in the mid-70s, he did a computer search to find this. So that's quite an early use of computers in the way that we would quite happily use them now. In fact, he gives a complete list of 76 arithmetic triangle groups when each of those P, Q, and R are finite, and 9 examples when one of them is infinite. What I want to do is sketch some of the examples. Right, okay, so this is just saying what I've just said, in fact, a moment ago. So let's do the example of 237. So we have the first 2 of these cosines, they're already integers. And so actually we're just getting a simple extension with 2 cos pi over 7. Remember, we're really interested in 2 cos 2 pi over 7. And that's exactly what this 237 is. This L of 237. And so I can slightly adjust my quadratic form and my generators so that all of the entries lie in Z of 2 cos 2 pi over 7. That's a little trick. And what I can see then is that my determinant, I can factorize my determinant, and it all hinges on this last term here. And because 2 pi over 7 is less than pi over 3, then this term is negative. Whereas because when I do the same thing with 4 pi over 7 and 6 pi over 7, because they're bigger than pi over 3, then they're going to be positive terms. And so I see that this group is arithmetic. There was nothing particularly special about 7. I can do this for 2, 3R. And then you can see that exactly the same argument is going to work. This is an exercise for you, works for these particular values of R. And that gives me the first 11 groups on Takeuchi's list. In particular, you'll see that the first, that it's necessary that R is bigger than 7 for it to be bigger than or equal to 7 for it to be a hyperbolic triangle. So the first example where this does not work is the 2, 3, 13 triangle group. And when I was asked for an image associated to this lecture, I asked for the tessellation, the 2, 3, 13 tessellation. And that's non-arithmetic since 4 over 13 is less than 1 over 3. And there's a very nice paper by Misha Belolipetsky, who used to be a colleague of mine here in Durham, who's now at IMPA in Brazil. This was a paper that he wrote while he was an undergraduate, talking about automorphisms of Riemann surfaces and exactly saying that this 2, 3, 13 group plays exactly the same role for non-arithmetic surfaces as the 2, 3, 7 group does for all surfaces. That's just a little throwaway in case people are interested in automorphisms of surfaces. When one of P, Q, and R is infinity, then we would have 2CP is 2, and then we can check that the product of the first 2 reflection generators has trace 3. I can just write it out, and I check that it has trace 3. And if it were the case that this number field that I was not equal to Q, then that would have a non-trivial Galois automorphism sigma. And since sigma preserves Q, we would have to see that when I apply this automorphism to A, I would still have trace 3. So that would imply that when I apply sigma to the quadratic form, I still have something of indefinite signature, because if I have SO3, the only element of SO3 with trace 3 is the identity. And so it must be the case that if I have an arithmetic triangle group where one of them is equal to infinity, then it must be that L infinity QR is equal to Q. And now you can do a little check and you find that there are 9 examples, and I've listed them there. So this is a special case of something called Goldmans Criteria, which is a much more general version of the same thing. Okay, I have 2 minutes. Let me very, very quickly show you how Takeuchi did this and connect it with the quaternion algebras that you saw in Bram's lectures last week. Okay, so Takeuchi views the group now as a subgroup of SL2R. I've been thinking of it as SO21, or a particular incarnation of SO21. He then views SL2R as a subset of R4, where the quadratic form AD minus BC takes the value -1. So this is some sort of quadric in in R4. He takes the three generators with traces 2CP, 2CQ, 2CR respectively, and their product is minus the identity. It's necessary that the product of the three traces times the identity is negative, or rather the trace of the, anyway, it has to fuss around with minus signs. He then shows that the identity in ABC is a basis for this triangle group over the in the space of 2 by 2 matrices. Thinking of the space of 2 by 2 matrices as a 4-dimensional vector space. Okay, and then in fact he shows that you get an integer linear combination for anything in the group. So I've just given a couple of examples of how you would write down particular elements in the group as an integer linear combinations of my basis. So that gives you the structure of the quaternion algebra. I'm not going to go into the definition of the quaternion algebra because Bram did that last week. And in fact, because the entries are integers, it's an order in the quaternion algebra. And again, Bram talked about that last week. But the key thing here is the determinant is a quadratic form. Remember I said that it's like A, B, C, D, preserve this quadratic form. Now there's a main involution in the group and in the algebra, which sends a matrix to its inverse. And the way these quaternion algebras are set up is what you do, what you realize that is you send each of the individuals of the identity A, B, C to their inverses, and you get the same linear combination. You can think of this as a little bit like my Galois automorphism on the rings of integers. Now I want to calculate x inverse x, and effectively I'm turning this into a quadratic form over this vector space. And so it's given by a symmetric matrix, and you can check, and Takeuchi checks that the symmetric matrix is given by, or 2 times that, is given by this 4 by 4 symmetric matrix. So that determines a quadratic form. Its entries lie in the ring of integers. It's clear that the traces do, that was by construction, and all you have to do is check that these other ones do, and it's a little bit of sorting out using trace identities. Now, if D has has indefinite signature, we get this determinant, we get this quadratic. If D is positive definite, then what's actually happening here is we're getting a quaternion algebra that's like Hamilton's quaternions, and then this is just the usual inner product on R4, thinking of the Hamilton's quaternions as being R4. And so arithmeticity is equivalent to showing that any non-trivial Galois automorphism leads to a positive definite form. Okay. And then Takeuchi needs to look at this matrix, and he shows you that it either has signature 4, 0 or signature 2, 2. That means either 4 positive eigenvalues or 2 positives and 2 negatives. And that's determined exactly by the determinant of the 3 by 3 minor, which is the favorite expression that we've seen before. And so he shows that this condition on this 3 by 3 minor is exactly the same as the one we saw on the determinant of our quadratic form. Again, he shows we can do better. And he talks about a different quaternion algebra now, where we instead of having A, B, and C, we have A squared, B squared, and their product. And we run the same machinery by, and we see that we're now working over the same L as we had before, and we only need to consider automorphisms non-trivial and L. So this is what Takeuchi says. It's exactly the same statement we had before. Now he's doing it using quaternion algebras. And so what I've tried to do, in summary, I think I've tried to pack slightly too much into this talk, and apologies for that. It is recorded. The slides will be available, but just to say, we want to show discreteness. Arithmeticity is a complicated machine that uses the discreteness of the integers inside the reals to show discreteness. And in the practical examples that we're thinking about, which are usually triangle groups, because this is a special semester all about triangle groups, we can either use the Gram matrix to give me a quadratic form and work over SO21, or we can use the generators and the identity to define a quaternion algebra over and then use the determinant. In both cases, we can use this number theory trick to show discreteness for a finite number of triangle groups. Takeuchi gives you the list. So, but in some sense, this is good news if we like geometry, because the remaining infinitely many triangle groups, we have to use geometry. Okay, I don't think this has been quite the best lecture I've ever given. I would like to apologize for that, and I welcome questions. Thank you.
Is this last slide or there is more slides remaining here? You are.
Sorry, say again?
Is it last slide or you have more material to?
No, that is the last slide.
Okay, okay.
So my goal was to get to Takeuchi's theorem a la Takeuchi, as well as getting to Takeuchi's theorem a la Vinberg.
So he classified these 85 triangle groups in 19 commensurability classes, right?
So he, yeah, so whoops, he gave you what, how, so you said the nine, right. So he gave us 76 compact triangles that are arithmetic, and 9 which are non-compact. So they have a vertex, an ideal vertex. And in fact, getting the complete list of the ideal ones or semi-ideal ones is easier than the compact ones, because of this fact that I said here, that the only element in SO21 with trace 3 is the identity. In SO3 with trace 3 is the identity. But the product of a pair of reflections in edges that end in an ideal vertex must be parabolic, and so it must have trace 3. And so therefore, and that's non-trivial. When I apply a Galois automorphism, I still keep trace 3. It's not the identity, and therefore I can't possibly be positive definite.
So, John?
Yeah?
Yeah. Is there a complex hyperbolic version of this theorem? Takeuchi's theorem? For SU2, I mean, for maybe triangle group representation inside SU2, 1?
Yes and no, in the sense that we have, so the construction, we can follow that very similarly. There are extra parameters that come in, and we have we have a finite list of possible groups that arise in this way. I'm not quite sure whether I'm actually implicitly this is with conjecture, or actually I think there's a so it's yeah. You can run the same game, but it's more complicated. All the non-arithmetic subgroups of SO21 that we know about arise in this way.
Oh, I see. So this is the way you constructed the fundamental domain. I mean, using these ideas.
So we have to use fundamental domains because we cannot use arithmeticity.
Because you want to construct non-arithmetic.
I wanted to construct non-arithmetic ones.
Okay.
So we have a list of arithmetic examples, and just because there's extra parameters, it just depends on quite where. Yeah, I think we have to, if we impose some extra conditions, we have a list of all the examples. If you weaken those conditions, I think there may be still more to be found.
Okay.
But it's a slightly different game.
Okay.
What is the 19 commensurability classes of the 85 triangle groups?
Right. So there's this. That is a good point. I didn't talk about commensurability classes here. So Takeuchi gives you 76 triangle groups, but some of them are commensurable to each other. And then there was a subsequent paper, which was not among the ones I listed, where he divided them into commensurability classes. But if there are finitely many triangle groups, there are certainly finitely many commensurability classes. Maybe somebody else could give another lecture on that. I think it's a beautiful paper, this Takeuchi paper, and I would recommend people to read it. It's a little bit hard going in places, but the mathematics is really beautiful. And what I hope I've done is given you a little bit of a window into how to think about it in a slightly different way. But many of the calculations, in particular, the fact that there are finitely many, I think this is a good exercise to really work through for yourself.
Percent of the triangle group in a same commensurability class have just similar geometric property or same, or what? Geometrically, how they will behave? Like quotients of the commensurable triangle groups.
So yes, there are. I haven't looked at what the commensurability of the different arithmetic triangle groups are, but yes. So some of these examples are commensurable to each other. So, for example, if I come down to this list here, you can see that let's see, 2, 3 infinity we know is going to be commensurable with 2 infinity, infinity, and 3 infinity, and infinity, infinity, infinity. So I think you basically are getting the 3s and the 4s and the 6s forming separate classes. I think it is. Off the top of my head.
Yeah. Okay, I think, thank you very much.
Thank you very much.
Okay, thank you.
If there are no further questions, maybe I would like to ask one simple question. How does one determine the reflection generator, which you have written down, or there is an algorithm for them? Or...
Yeah, I can show you. It's very easy. Let me find the right page. Whoops, I've opened to the wrong page here. Why did I write it down here? Blah, 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 blah. Here we are. Okay, so let's just think about what the formula for a reflection that we would normally have. So what we would normally do is that we would write x as x dot n times n plus x minus x dot n times n. And I guess I probably ought to put an n dot n in case I'm not a unit normal. And I should say, right, so that's what x is. And now to get a reflection, I reverse the sign of the thing that's orthogonal. So I put a minus sign here. Okay.
Okay.
And now if I replace this dot product with the thing that I had with my gram matrix, and so I could write this as being x n over n, and there's actually two of those minus x. Now, so then if I were to take this to n1, for example, to be this, then what I'm going to get, let me erase that, so I've got some space I should have left some more space. People who are much more used to doing online talks leave a lot more space than me. So what I can do is, let me get this right, is that I can write this as n transpose 2g, I think I want two of those, minus the identity divided by n transpose 2g n. Okay, so let's look at what that would be. So that's basically writing, just extracting this x out of here. And so I'm going to have, I'd have like 1 0 0 1 0 0 times my 2g. So what that does, it just picks up the top row of my 2g. So I could write that as 2
minus 2CP and minus 2CR.
Okay, and then I need to have that times n. So I need to times 1 0 0. I'm sorry, I've got that. Anyway, so you use that formula, and so you're going to get sort of a 2 here, that entry, and then you have to do minus the identity there. So you're going to get 2 minus 1 is 1.
Okay.
And similarly for the other ones. It's just simply using this usual formula for reflection, but with the gram matrix.
Okay, okay. Thank you. So are there any further questions? If not, I take this opportunity to thank the speaker very much for the very positive, definite talk in these difficult COVID times. And it was also a very colorful talk. Thank you again for your lecture, and thank you for enlightening us on Takeuchi's theorem, 2 ways, using quadratic forms and using algebraic number fields also. So thank you very much.
Okay, well, thank you very much indeed. It's been a pleasure.
Okay, so we have a break now.